Welcome! Today we start Unit 11, Exponential Functions, and Day 1 is Laws of Exponents. This is section R2 in the textbook, and in particular, just one objective we're going to focus on, use the laws of exponents. Here we go. Basic exponential rules. Here we go. These are the basics. So the definition of a to the n just means multiply a times itself n times. So 5 cubed, for example, equals 5 times 5 times 5, which is 125. Now, it turns out that any number raised to the 0 power equals 1. So, for example, 5 to the 0 equals 1, or 18 to the 0 equals 1, or 97.2 raised to the 0 equals 1. The only exception to this is a can't equal 0. Now, a to the negative n, that means 1 over a to the n. So, for example, 5 to the negative 2 really means 1 over 5 squared, which is 1/25. There's a nice way to actually see why this works. Let's say 5 cubed is 125. And what if I divide by 5? So 125 divided by 5, so divided by 5, that gives me 25. Oh, and that's 5 squared. And what if I divide by 5 again? 25 divided by 5 is 5, and that's just 5 to the 1 power. Now what if I take 5 and I divide by 5 again? I end up just with 1, because 5 divided by 5 is 1. And we can see on top the pattern continues. 5 to the third, 5 to the second, 5 to the first, 5 to the 0. So by looking at the pattern, at least it seems reasonable that 5 to the 0 should equal 1. And what if I keep on going? What if I take 1 and I divide by 5? I get 1/5. And on top, if I continue the pattern, that would be 5 to the negative 1. Divide by 5 again, it turns out I get 1/25, and on top 5 to the negative 2, and so on. So that's the idea. And so you can see, even though it seems strange for people that a to the 0, a number to the 0 should equal 1, or a number to the negative power should mean a reciprocal 1 over something, actually, it kind of makes sense. Let's do some example using those rules. I encourage you, please, stop the video at any time and see if you can work out the solutions to these before I do. All right, here we go. First one, evaluate negative 5 squared. The parentheses are important, so that's negative 5 times negative 5. And so negative times negative is positive, and that's 25. But take a look to the right. How about evaluate negative 5 squared? Remember the order of operations, PEMDAS. PEMDAS, or please excuse my dear Aunt Sally. The exponents come before multiplication, and putting a negative out in front is like multiplication. It's like multiplying by negative 1. So the square, that exponent, that applies only to the 5. So the solution should be negative of 5 squared, so negative 25. All right, moving on. How about 6 to the negative 2? Well, based on our rules on the previous slide, that should be 1 over 6 squared, which is 1/36. Negative 4 to the negative 2. Again, does that negative 2 apply to the negative in front? No, it doesn't. The negative power of 2 only applies to the 4. So this becomes 4 to the negative 2 is 1 over 4 squared, and that negative stays out in front. So in other words, negative 1/16. All right, how about this next one? 2 to the negative 3 times 2 to the 4. Well, 2 to the negative 3 is 1 over 2 cubed, and 2 to the 4 is just 2 to the 4. And now I could multiply those two fractions together and get 2 to the 4 over 2 cubed. Now there is some canceling that goes on here. On top, I really have 4 factors of 2. So 2 times 2 times 2 times 2. And on the bottom I have 3 factors of 2. 2 times 2 times 2. And so common factors can cancel. 2 over 2, 2 over 2, 2 over 2. So it looks like I'm just left with 2. And how about this last one? Simplify 2/3 to the negative 1. So that's 1 over 2/3 to the positive power 1. Or in other words, just 1 over 2/3. Now, when I divide by a fraction, it's the same thing as multiplying times the reciprocal. So that's the same thing as 1 times 3/2. Oh, which is just 3/2. There we go. Here are some laws of exponents. These are rules that just come up again and again and again when we work with exponents. Let's take a look at each of these. So number 1, a to the m times a to the n equals a to the m plus n. So for example, how about x squared times x cubed? Well, x squared is really just x times x, and x cubed is x times x times x. So look at that. How many x's do I have? 1, 2, 3, 4, 5. I have 5 x's altogether. And so, yeah, the 2 plus 3, that's the 5. How about the next one? What if I have x squared and then that gets cubed? So that's the same thing as x squared times x squared times x squared. But then each x squared is really just x times x. So that is x times x times x times x times x times x. And how many x's do I have? I have 6 x's. So x to the 6, which agrees with the rule. So 2 times 3 is 6. So when you see exponents that are sort of on the same level, like x to the 2 and x to the 3, then they add together. But when you see exponents on top of exponents, something that's squared and then cubed, that's when exponents multiply together. Now sometimes you can have different bases. So far I've had the same base, just x. But what if I have x and y, all of that raised to the 3rd power? Well, that's the same thing as xy times xy times xy. But this is all multiplication, and multiplication is commutative, so I can move all the x's in front, x times x times x, and all the y's on the right, y times y times y, and that's x cubed times y cubed. So you see, you can distribute exponents over multiplication. The x and y are being multiplied, and it's important, not added, they're being multiplied. And so the 3 distributes over that multiplication to give me x cubed times y cubed. How about another example here? What if I had x to the 5th over x squared? All right, so I have 5 x's on top, 1, 2, 3, 4, 5. I have 2 x's on the bottom, 1, 2. And so what happens is that there's a certain amount of canceling. 2 of the x's go away, leaving me with an x cubed. So I have 5 minus 2 equals 3. And that's how the rule works. And then lastly, let's just say I have x over y, and that whole thing is being cubed. Well, of course, that's the same thing as x over y times x over y times x over y. And how do you multiply fractions? You multiply the top, x cubed. You multiply the bottoms, y cubed. And so there's our solution. And so also, it looks like with a division problem, this exponent distributes over division. So this becomes a to the n over b to the n. Just like I had x over y to the 3, it's x to the 3 over y to the 3. Let's continue to use these laws of exponents in several examples. Now, when we simplify, our goal is often to rewrite so that all the exponents are positive. Let's see if we can do that. In this first case, x times y to the negative 3 over z. Well, maybe I could pull the y out to the right. So that's the same as x over z times y to the negative 3. And then I can use the fact that y to the negative 3 is 1 over y cubed. And so I end up with x on top and z y cubed on the bottom. Now be sure you try these problems before I do them. Maybe pause the video if you need to, and take some time and really think about these things, and then check your work with my solution. Now something happens here. Look at this. This y was raised to the -3, and it lived on top of the fraction, and then it changed into a y to the +3 on the bottom of the fraction. And when I moved it from the top to the bottom, that -3 turned into a +3. Meanwhile, the x and the z just stayed exactly where they are. The x stayed on top, and the z stayed on bottom. So we see this a lot. That when a variable changes position from either the top to the bottom or the bottom to the top, its exponent will be negated. Let me think of another example. How about 2x to the 7 over 5? That ends up being the same thing as 2 over 5x to the -7. Or if I have x z to the 4 over m, all right, that's the same thing as x over m z to the -4. Or if I have y over x to the -7, that's the same thing as y times x to the 7. All right, let's continue on. Example number 2. X to the 5th, y to the -2 over x cubed y. So maybe based on the discussion we just had, we can take that y to the -2 and just pull it down and make it a positive exponent. So this becomes x to the 5th, and then on the bottom, x cubed y squared. And then now I can combine the y and the y squared, and that becomes y cubed. All right. There's another way to do this. Let's say I separate the x part first. So I have x to the 5 over x cubed, and I multiply that times y to the -2 over y. And then I can use my exponent subtraction law. So I subtract exponents. So on the first, I get x to the 5 minus 3. And on the second factor, I get y to the -2 minus 1. -2 minus 1. And so that's x squared times y to the -3. Oh, and that's the same thing as x squared over y cubed. And that makes me realize I forgot some simplification earlier on. This x to the 5 over x cubed, that should have been simplified further, giving me x squared on top and y cubed on the bottom. All right, it's all simplified now. That's good. A couple more examples. I can distribute that power of 2 across multiplication. Now, again, if this was addition in here, I couldn't do it, but since it's all multiplication, I can. And so it becomes x squared times y to the -3 squared times z to the 4th squared. And then I have exponents on top of exponents in a couple places, so let's simplify that. So that's x squared times y to the -6 times z to the 8. And then finally, let's take this y to the -6 and write it as 1 over y to the 6. And so that leaves me on top x squared z to the 8, and then on the bottom y to the +6. Example 4, I'll distribute the 3 above and below on both parts of the fraction. So I get 2x cubed over 3y to the -2 cubed. Then I can distribute the exponent of 3 on each of the factors. So 2 cubed x cubed, and then 3 cubed, and then should I just go ahead and multiply the exponent out? So this becomes y to the -6, y to the -6, like that. All right, so 2 cubed is 8, so I get 8x cubed. 3 cubed is 27, so that's 27. And then y to the negative 6. Well, how about if I just take this guy and use this trick where I bring that y to the negative 6 up, and I'll change the negative 6 into a positive 6. So y to the 6, just like that. Example 5. Rewrite so that all exponents are positive. So once again, it looks like I can do my my movement trick, moving a couple of these up to the top, in which case I get x cubed z to the 5th all over w squared y to the 4th. Now, if I had done this the longer way, the more, quote, official way, I might do this like 1 over w squared 1 over x cubed times y to the 4th times 1 over z to the 5. All right, and then that equals, in the denominator, it looks like I get w squared y to the 4th, w squared y to the 4th over x cubed z to the 5th, x cubed z to the 5th. And then when I divide by a fraction, it's the same thing as multiplying times the reciprocal. So that gives me 1 times x cubed z to the 5 over w squared y to the 4. And so 1 times, so of course I can just erase that. And look, of course it's the same thing that I have in both places. So if you can remember that little trick, that whenever you move a variable with an exponent from one side of the fraction bar to the other, then its exponent negates. So that's just a good trick to remember. In example number 6, I have a negative 3 as my exponent, but that's okay. I'll distribute that just like I've done before. And so I get 2x to the negative 4 to the negative 3 all over 3y to the negative 4 to the negative 3. So I get 2 to the negative 3. Then how about this next one? X to the negative 4 raised to the negative 3. So maybe x to the positive 12. And 3 raised to the negative 3. And then again y, but it's to the negative 4 times negative 3. So y to the 12. And then maybe I'll use my switching trick. So this 3 to the negative 3 becomes a 3 to the positive 3 if I bring it up on top. X to the 12 stays there. 2 to the negative 3 becomes 2 to the positive 3 down below, and I get a y to the 12 there. And then I can simplify those numbers. So that gives me 27 x to the 12 over 8 y to the 12. All right, there we go. So this is it. This is Unit 11, Day 1, Laws of Exponents. Just a few rules to keep in mind, but they take some good practice to get a hold of. So if you need the review, be sure to check back over this lecture and try those problems again. Make sure everything is clear. All right, and this is a good place to stop.